Hey, welcome back to my Introduction to Mathematical Proofs playlist. Today we'll be talking about composition. We'll continue to talk about functions. That's what we talked about last time with bijections. And particularly, we're going to be looking at a specific thing, function composition, or the art of combining functions. Then we'll see how function composition is related to injectivity, surjectivity, and bijectivity. But first, let's show you a visual. You might remember this diagram from before. All we're doing is making the map from A to B so that it's a bijection. But now what we're going to do is we're going to add in a set C, and our C is going to have completely different values, and then make a map from B to C. We're going to call that function G, so G goes from B to C, so that it is also a bijection. What we want is a function that goes from A to C directly, as in applying one, then applying the other. That's what function composition means. You apply one function, then you apply the next function. There's two things to note here, just before we get into the nitty gritty. In this case, A and B and C are completely different. This is so that there's no confusion, but later on this might be the case when you're doing worksheets or problems, so you know. And yes, both functions are bijective for now. Don't worry, we'll deal with that later. So we're just gonna import it in here, and look, it's so nice. The idea is this: we want a function h that goes from A to C, that uses the function f and uses the function g. So we have to apply one function, then the next function. Now the question is, what do we apply first? Do we apply f and then g, or g and then f? What we'll notice is that our function h goes from A to C, but our function f takes elements from A and puts them into B. So it makes sense that the first thing we'd have to do in order to make a function that goes from A to C is first apply f to get elements from A to B. Then we can apply g that takes elements from B to C. So we say that h of x is equal to g of f of x. What's on the inside is applied first. So f of x is applied first, then it's g of x. Or we use this little circle here that's empty in the middle to denote function composition. So g compose f of x. Or if we don't have the x at all, it's just h is equal to g compose f. G compose f is not the same as f compose g. These are completely different things. In fact, f of g, so applying g then f doesn't make sense. Because how does that work? Well, if you apply g first, it takes elements from B to C, but then f doesn't take elements from C at all. So that literally does not make sense. And secondly, we read from right to left. So g compose f is the same as saying we apply f and then apply g. It's really weird. We apply right to left, or from inside to outside whenever we're using the f of x and g of x notation. This is kind of annoying and kind of confusing. Even I get tripped up. So keep in mind, g compose f means we apply f first and then g. We read from right to left. Now what's really weird is that in our diagram we go from left to right, so that's why, it gets a little confusing and annoying. But to make sure that we understand what's happening, let's just run through a few examples. So h of 1, well, h of 1, we first apply f, so 1 goes to b, then we apply g, b goes to negative 1. So h of 1 should be negative 1. H of 2, well, f of 2 is a, g of a is negative 3, so h of 2 is negative 3. Then h of 4, well, f of 4 is d. G of d is negative 5, so h of 4 is negative 5. Make sure you understand exactly what's happening here. Hopefully this is enough of a foray into function composition. We'll now look at how bijections work. So we're going to think about h inverse. So we see that f and g are both bijections. So we know that f inverse and g inverse exist. But what about h inverse? Does h inverse exist? Well, intuitively, if we can map an element from A to C via h in a unique way, then h is a bijection and should be invertible. So the first thing we're going to show is that if f and g are both bijective, then g compose f, which is the same as h, is also bijective. And we're going to prove this. And for the sake of notation, we're going to let h equal g compose f. Now, we're going to start with injectivity. What we're trying to show is that if x1 is not equal to x2, then h of x1 is not equal to h of x2. So, you just run through it. x1 is not equal to x2, but then since f is injective, this is the same as saying that f of x1 is not equal to f of x2. But since g is injective, this is the same as saying g of f of x1 is not equal to g of f of x2. But then g of f is the same as h. So h of x1 is not equal to h of x2. And what's really interesting here is that we only require f and g to be injective. So we also proved this lemma. A lemma is kind of like a small proof or a side proof that's usually not that hard. And it's this. If f goes from A to B and g goes from B to C are both injective, then g compose f is also injective. G compose f, once again, we apply f first, then g. Now let's look at surjectivity. Let z be an element of C. Then we're going to let x equal f inverse of G inverse of C. This is really weird, but we know that the inverses exist because f and g are bijective. So we have that h of x is the same as g of f of x, but then x is the same as f inverse g inverse z. So in total, we have g of f inverse of g inverse of z. But because how inverse functions work, f and f inverse cancel out, or f compose f inverse cancel out. So we get g compose g inverse of z. But once again, g and g inverse cancel out, so we get z. So h of x is equal to z. So we have that since h is both injective and surjective, h must also be bijective. And this is kind of a formal note. Technically, we can show that if f goes from a to b and g goes from b to c, if both of them are surjective, then g compose f is also surjective. And this slide right here has everything you need to know, but I won't go too deep into that. Okay, so we prove the following. If f goes from a to b and g goes from b to c, well, if f and g are both something, then g compose f is also the exact same something. So they're both injective, then the composition is injective, both surjective, composition is surjective, both bijective, composition is bijective. Now that we know that h is a bijection, we know that it's invertible. So what would h inverse b? Well, as you remember from last video, it's usually what's in our surjectivity proof. So we have that h inverse is f inverse compose g inverse. So think about this. This is really weird. Even though h is g compose f, the order of h inverse is actually reversed. It's f inverse compose g inverse. Once again, it all comes down to how the codomain and the domain line up. G inverse's domain is C. Since H inverse's domain is also C, we must have that we apply G inverse first. So the rule of thumb is this. If H is G compose F, then when you invert it, you actually flip G and F and invert both of them. So now let's just run through some examples of the inverse function. So what's H inverse of -1? Well, let's start all the way on the right in C. So we have -1, and then we take the arrow back, because that's what G inverse is. So -1 goes to B. Then we take the arrow back in the opposite direction via F inverse, so B goes to 1. So H inverse of -1 is 1. H inverse of -3, well, -3 goes to A. If we take the arrow back, which goes to 2, so H inverse of -3 is 2. And let's look at H inverse of -4. Well, -4, if we apply G inverse, we go to E. If we apply F inverse, we go to 5. So H inverse -4 is 5. And once again, here's all the algebra, just so that you can see exactly what's happening here. Lastly, we'll look at an interesting problem. If we know that the composition of G and F, or H, is a bijection, what can we say about F and G? What are the least restrictive conditions on F and G so that H could be a bijection? Note that this is different than what we solved before. Before, we had assumption about F and G and try to prove something about H. This is in the exact opposite direction. If we have something about H, what do we know about G and F? So what's really weird is that you can try to think of the first question as a for all statement, as in, okay, we know that if F and G are bijections, we're guaranteed that H is a bijection, where this question is the exact opposite. If we know that H is a bijection, what conditions do we need to have on G and F so that H can be a bijection, or there exists? So let's actually start with G. We know that H goes from A to C, but we also know that G goes from B to C. So in order for H to reach all of C, we must have that G must be surjective. And to prove this, we'll assume that G isn't surjective. Then the range of H is a subset of the range of G. You should think about why this is true. Because B is in between A and C, we kind of really don't know if every single value in B will end up appearing when we apply H, for example. But then clearly, since G is not surjective by contradiction, range of G is not equal to codomain of G. But then this means that the range of H will never be the codomain of H, and the codomain of G is the same as the codomain of H, since they're both C. So C would never be bijective, but this is a contradiction since we assume that H is a bijection. Now, let's look at injectivity. Well, if you say that G is not injective, then you might be able to be like, okay, maybe we can find some pair, x1 and x2, so that f of x1 is equal to f of x2, and then we'll come up with some contradiction. But that's actually not true. If we introduce an extra point f in B and map it to something in C, let's say -4, well then you'll notice that this is the exact same thing as before. Do you see it? The composition, H, which is G compose F, will still be bijective even though we added a point in B that maps to a point in C. So B is now not injective, but the composition is still bijective. So we would never be able to prove this because we found an example where G is only surjective and not injective, the composition is still a bijection. Now, if you don't believe me, this composition is a bijection, try it for yourself and see, and you'll notice that indeed this is still a bijection. So all we did was add a point in F, and H was still biject. Nice. But let's look at F formally and see what happens here. I claim that F must be injective. So for the sake of contradiction, we're going to assume that F is not injective. Then we can find some x1 not equal to x2 so that f of x1 is equal to f of x2. And for the sake of notation, we're going to let y equal to f of x1, which is equal to f of x2. Now, since h is bijective, we have that x1 not equal to x2 implies that h of x1 is not equal to h of x2. So we'll just start with h of x1 not equal to h of x2. Then we'll apply the composition. G of f of x1 is not equal to g of f of x2. But then since f of x1 is equal to f of x2, which is equal to y, we get that g of y is not equal to g of y. That's a contradiction, since functions only map to one element. There's no way that this could be true. Thus, f must be injective. But once again, f doesn't need to be surjective as we saw before. Now, we're going to look back at the function and show you something really, really interesting. We agree that the composition now, at this current state, is a bijection. But if we just change a simple arrow by sending 4 to f instead, this is not a bijection anymore. Since both h of 4 will get to negative 4 and h of 5 will also get to negative 4. This is not a bijection anymore. This actually breaks both injectivity and surjectivity. This is very, very important, okay? Just because G composed F is bijective and we showed that G must be surjective and F must be injective, this is not the same as saying that if G is surjective and F is injective, then the composition is bijective. This is not reversible. An implication, this implication only goes in one direction. This is not an if and only if. Before, what conditions do we need to have on F and G? Well, we need to have that F and G are both bijections, then their composition is a bijection. So you have to be careful. Implications are not the same as if and only ifs, and make sure that you don't get this mixed up. Maybe now you'll be fine, but maybe in a day or a week or when you do a test, for example, this is something that'll slip, something that you won't remember. This is something you have to keep in mind. Once again, one of these forces condition on H, while the other one forces a condition on F and G. Okay, that's actually all there is to this video. Till then, I will see you later. Bye.